computer. And so, hello everyone. Just as a warning before I start, I have a minor cold, so my voice is going to be even worse than usual. But I think I can make it until the end of the talk. So let's try. So today is day 7 of the tutorial, and today we're going to learn how to perform non-NLTE synthesis with DeSIRe in parallel. Okay, so we are going to start from the atmosphere that we created in our age tutorial. It was the number 10. And it was an atmosphere that we extracted from the enhanced network simulation run. It was a snapshot 385. And what we did was we used the atmosphere for computing the optical depth at 500 nanometers. And then with that, we create a file that was that optical depth plus the atmospheric parameters in the DeSIRe units and also interpolated to a uniform optical depth grid. So in that class, we did both things. So we computed optical depth and we also prepared everything for the DeSIRe tutorial. So then this one is going to be a bit faster. Also, I think most of you are familiar with the Python wrap because it's the same one we use in the DeSIRe course and also in the RH tutorial. So today I'm just going to cover it slightly. So we are going to prepare the configuration files and check some things, but I'm not going to really explain it in detail. But if you have any questions, just let me know. Just send me an email or just ask them in class, and then I will just help you. Okay, so then there's nothing special. So then we can just go to the tutorial. So we are going to I'm going to share with you this folder that is called parallel synthesis. And inside you have different things. You have 2 folders. Then you have some help regarding the Python wrap. This is the Python wrap itself. This is some information and some executable for installing it that Ricardo prepared. This is let's say, the control file for the parallel wrap. And this is the atmosphere that we created in class. So today we are going to check this initialization file, and then we are going to go to results. And I already prepared the run for the synthesis. And this run one is the folder that you need to check when you are checking the class. So here there's a lot of things, and there are 2 IDL scripts, okay? So then let's go to check this one, and we are going to move back and forward on this folder. Okay, so this is the ideal procedure that we are going to check today. So the idea is that, as I said, we are going to use the atmosphere that we adapted from our age output in day 10. We use this procedure. So in case you just want to take a quick look, I put it also here, but we are not going to run it. It's just if you want to check it. And the idea is, if you have any question, just let me know. And also we are going to have the same configuration of day 5, except I just increase a bit the spectral coverage of the calcium lines because I felt that it was a bit narrow in that configuration. And now a Q wing is a bit larger, but this is the only change I made respect to the other configurations. Okay, so then let's start with running the code in parallel. So for that, we go back and we are here and we open this initialization.input. That is the file that we have here. Oops, we had it there. Just let me open again. So it's this one, and it's very simple. So the important thing is that you have a few lines and you should check what you have in the first part inside brackets. So S is from DeSIRe, D is from DeSIRe, M is from Modelador, and R is from RH. So if we are using DeSIRe, you have to fill the lines that contain D inside brackets, while the other lines are not necessary in this case. So for example, in this case, this line is related to which type of height scale you use in RH, and we are not using this in DeSIRe, so you don't need to worry about that. Okay, so then for the synthesis, what we need to do is to set the number of cores of our server, then the input atmosphere. In this case, I put it here just to simplify everything. Sorry. And then the number of pixels we want to synthesize. So in the example that you have in the run1 folder, I did it for the full snapshot, for the full small piece of the snapshot that we use in the RH class. But now I put just these numbers just to run it on class. But in the case of the example that we will check later is the 230 times 230 pixels that we selected for RH tutorial. And it's the same field of view that we use in the paper. Then here, yes.
Carlos?
Yes.
So 0 to 5 means 5 positions or 6 positions?
6. So yeah, so I think if you want just 1 pixel, I think it should be like this.
Mm-hmm.
And in this case, it will be, I think 6, because if I do this, it says 36 core, so it's 6 times 6 pixels.
Okay.
Yes, Ricardo, this is correct, right?
Yes.
Okay, thank you. So
it's in the Python scheme, so you start with 0 and go.
Okay.
So,
yep. So then I think in this case, it's the same things that we covered. So just let's go ahead. In this case, it says D from this side, but this is for the inversion. So in synthesis, it doesn't matter what you put here. And then I think the most important thing in this case is this path. So you have to put the DeSIRe path. In my case, I copy another DeSIRe distribution just to have things organized. But the important thing is that if you remember, we were running different examples in the folder run of DeSIRe. But for the parallel wrap, what you want to provide here is the location of the executable file. So then it should be a bin folder. Don't get confused for that. And then the rest of the things are this. So with this, you can run the code. And as I show you here, basically, if you have enough cores, you can run this in one go, and it takes around 7 seconds per pixel. And this is the full NLTE solution. Okay, so then just let me make this a bit smaller because Zoom is in the middle. Yes, here, sorry. So then with that, we can run the code. And what I did was run it for the full map. So just, sorry, let me go back. So what I did was to run it with this configuration. So if you put 1 and let's just comment the other, with this, you can run it for the full map. And then the results, they appeared here, but I moved them to this folder, run1. Okay, so inside you have the results from the synthesis, the programs that we are going to use now for analyze the data. And then I always do the same, and I create a folder in where I have the results of the run. And here I copy all the files that I use for the synthesis. So it means that I copy run files and all the elements. So if you see, this is a copy of what you have here, except results and the input atmosphere. And this is because mainly in inversions, you change things and you want to compare one result with another. So my recommendation is always try to save also the configuration you use, because if suddenly you realize that one configuration was much better, but you don't remember the number of nodes or what did you change, then it's going to be very difficult to replicate it. So always, if you change something, I don't know, the initial atmosphere or the nodes or something, just copy that information.
Carlos, sorry for interrupting.
Yes.
You also have this information on the PDF file that.
Yes, at the end.
So.
But this is for inversions, right?
For inversion, I think it's for synthesis, but I can recheck if it's there, but I can include it easily. Yeah.
Yes, and also this contains what is mainly DeSIRE in terms of the role, but not the atoms or keyword.input or...
Keyword.input is also there. The atom,
Okay.
no, but I can include it if you think that is a significant thing.
Yeah, I think it depends on the user. For me, I like to copy everything, but but maybe it's better if we do it. So it's a good thing. Yes, let me take note of that. So include configuration files, notes. Yeah, I think it's better to have it also, but at least my advice is at least you can follow this approach and copy everything here. Okay, so then before checking the results, just as a double check, so we change this one, and then inside RIME files, we have essentially the same files that we use in day 5. So we have the wave read, the keyword.input, the control file. These 3 go here. And also, if you are using weights, you have to put it here. We will check this in the next class. And then Atmos contains the initial atmospheres that we are going to use in inversions, but in this case, is not used because we are doing synthesis. And then in input files, we have all the things related to RH and also sometimes to DeSIRE, but essentially abundance, the atoms, and then the atoms path, and then the atoms in itself. If you're using, you can have the ones you modify, you can put them here. And also the lines file for DeSIRE. So essentially, all the files that we were configuring in day 5 and before, they have to be here. I put a note, just 1 second, because Zoom is not making things easy today. So I put a note here that just some things are different, but so in terms of where things are, so in when we are running in DeSIRE folder run, we have a path that goes to sometimes a var or other places, but here is a bit different. So my recommendation is that if you want to run in parallel, just copy these files, this example completely. And then if you want to change something, so for example, you said, I want to change something in the keyword.input. So you just open this file and then you change, for example, the number of iterations, something like that. But I think it's better if you copy just this because it's already pointing to the files you want to use and also with the name that the parallel wrap is going to use. So this is my recommendation. So just copy this example and then change things internally, but don't bring the files from the serial computations that we did before. Okay, Ryan, yes?
Sorry, I don't know if this is just my screen, but on your screen, it's like some of the windows have slightly bugged and I can see like a disjointed window.
Yeah, the same happens to
That's
me.
happened to me as well.
Yeah.
Yes,
Okay.
if you just minimize and open that file.
Okay.
I think those are the Zoom small windows, Carlos. If you remove our view, probably they will disappear.
I think already
No,
is
I usually have it. So now is it better or
no.
not?
No,
No?
when you move the window,
Okay.
you have some
So-
memory of the old position.
Oh, okay. So if I stop sharing and then I share again, now is the same?
Now it's okay.
I know.
Okay. Is it okay if I move up and down?
Yes.
Yes.
Okay. Okay. Thank you. Yeah, I think also the laptop have some call and some issues. Okay, so then just let me move this a bit because I have a lot of pop-up things from Zoom. So let's see if I manage. Okay, so then I think it's fine. So then what I was saying is just copy everything, this package, and then if you want to change minor things internally, do it, but don't bring your files from the serial because it's not exactly the same. Just let me, yes, okay. So then we have run the code, you know more or less the files we use, you know where they are located. So then let's go to results. And then what you get is this file, okay? So this fits is the cube of data that it will be generated by the code, okay? So then we can read it in IDL, for example, we can use red fits. And then the idea is that if you use just red fits, it will be X and Y, the horizontal domain, and then wavelength, and then Stokes. So it will be, in this case, 4 Stokes parameters. So if you want to have information about the wavelength and the index related to the line, then you just use this instruction that probably in Python should be similar, and then you can get the information. So then the idea is that now we are going to, again, as always, separate the 3 windows that we have. So iron 630, calcium 8498, and calcium 8542. And then we have these cubes of data. And now, just as an example, I want to show you some spectral features to check how the synthesis went, and also to see more or less how the lines behave in non-LTE or LTE with this simulation. Okay, so then we're going to plot the continuum. That is essentially, as we are going, so for example, in this case, Stokes I, we have just picked all the wavelength points and then 0. So then now this Stokes I iron is X, Y, and wavelength. So then if we pick all the X and Y points and the wavelength 0, we are picking the continuum intensity. And then we are going to pick the line rest intensity. So for that, we print where the wavelength for the iron line blend is 0, and in this case is 70. So then at this index, we are at the rest of the line, in this case of the line 6301.5. Okay, so then we just pick all the X and Y points and only the line core intensity, the line core position. So it will be line core intensity at rest wavelength. And now we are going to do the same. So just to have an idea of how the linear polarization and Stokes V polarization signals behave. So we are going to run a loop. So for that, we need to know the dimensions of the array that I compute here. And then we need to create 2 arrays where we are going to store the information related with the linear polarization and the magnetogram. For both things, we need to have an idea of where our line of interest is. So in this case, I said that around 0 and 120, it's the region where the line 601.5 is located from the core to the wings, just to avoid mixing things with the iron 6302. And later on with between the calcium and the satellite lines. And then we are going to run a loop. This is one option for computing these features, but there's a lot of different ones, so you can pick others. But it's just to have an idea of how the synthetic spectra looks like. So in the case of linear polarization, what I did is compute the square root of the Q square plus U square. And then for the magnetogram, is just computing the Stokes V signals at a given position. In this case, is from the line core 7 pixels, that as the spectral sampling is 10 milliangstrom, this is 70 milliangstrom to the right and 70 milliangstrom to the left, so longer and shorter wavelength. And the idea is that it should be located close to the lobes of Stokes V at a rest wavelength. So if there's a shift, then things will probably get not as good. But if there's no strong velocity shift, then you should be more or less at the lobes of the Stokes V. So this is just as a reference, okay? So with that, let's make a plot. We have the value in terms of megameters for the simulation, the coordinates that we use for the synthesis, and then with that we can make this plot. And just let me show you. We have already them in Dropbox. So this is what we were computing. Maybe seeing them is easier than what I explained. So essentially, if we just pick the continuum, we have this granulation pattern. You have bright granules, you have dark intergranules, and then you have bright regions that correspond to concentrations, to strong concentrations of magnetic field. Then in the line core intensity, you have the reverse granulation. So granules now look dark, intergranules are brighter. And then the concentration, the regions with a strong magnetic field, they are still bright. And they look smooth. So we don't have any issues. There are no convergence issues. So the code is behaving well. Then linear polarization signals are located usually close to the concentration of magnetic field because this is network patch. Sometimes you have some inclined fields close to them. And I would say that is very, very nice. Just as a minor comment, sometimes you can see these small things like some kind of perturbations, maybe waves. And this is usually is not related to the code itself, it's related to the limited spatial resolution of simulations, either in the vertical domain or in the horizontal domain. So in general, these simulations, as they improve or increase the spatial resolution, those things tend to disappear, and sometimes they are very small, sometimes they just completely disappear. So if you see this, I think it's not a big issue, and it's usually more from the simulation side than the forward modeling side, but just I wanted to note it. And then in the case of magnetogram, also it looks very smooth and very nice, and you have that most of the patches, they are in this small field of view, they have one polarity, but as this network patch, so this simulation, it has two network patch of opposite polarities. So then in this side is where you have the opposite polarity patch. So you can see some opposite polarity patch here, but then if we had the full field of view, you will have more concentration here. But essentially we have this one, but you can see at some points they have reverse polarity. But in general, I would say that it looks smooth and it looks very nice. Okay, so then let's try to do the same in the program. I just did the same. So the continuum for the calcium lines is index 0 of the spectral window. Then I look for the index in each case. I'm sorry, I will try to reach the end of the class. So the point, the wavelength point where the wavelength is 0, both for the calcium 8498 window and 8542. And then I did the same for linear polarization and magnetogram. I defined a short region where you have the calcium lines. In the case of 8498, it's important that you precisely select that region because we have an iron line. Let me show it here. So you have this iron line here, and you don't want to compute the linear polarization in this window because otherwise you will be mixing the signals from the iron line and the calcium line. So try to cut only in this region. Even if you are not getting the wings, at least you are not getting affected by this line. And then it's the same for as we did for the iron line. So just go until the end and let's check the figures. So 8498 looks like this. So the continuum is almost the same. Maybe you have some minor differences because of the visible and the infrared, but it should be very minor. Then the line core intensity is very different because now we are seeing much more higher in the atmosphere. And in fact, it's not related at all with this pattern, but it's good. And you have a lot of dark areas where the line is very dark. It means the intensity is very low. And then you have also regions with bright, so higher intensity that it could be either magnetic field or some interaction in the atmosphere. And in general, I would say that we can expect realistic profiles from the simulation. Of course, there's always limitation, but I think they are not so bad. It is true that I didn't add microturbulence just to keep things simple, but all the works that have used this simulation, they pointed out that there's a lack of small scale velocities that will make profiles too narrow, and then it will enhance also the polarization signals compared to what we have in the sun. But for this example, I didn't want to enter that. So even if the profiles are less realistic, what we are just checking is how to run the synthesis and then how to do the inversion. So don't feel too worried about that. And then the same with the other two parameters. So linear polarization is very complex, and this is because the magnetic field in upper layers is different than what we have here. And then this, I'm not sure if we can call this magnetogram because the line curve of the line, so the line curve, the calcium lines, they move so fast that fixing one wavelength and then checking the Stokes signals at fixed wavelength compared to that, we are probably mixing things. So I would just say that this is some idea of Stokes signals, but I'm not so sure if this should be a magnetogram. But it probably is better to move with the line. But that is also another thing that could be risky. But just as an idea, following the same procedure, you get this pattern. Okay. And then with the calcium line, the other line is different. That is good because it means combining both lines, you can get different spectral features probably and different information of the atmosphere, but the general idea is the same. So continuum is similar, but the line core intensity and the other parameters, they look different because they are, in the case of the line core wavelengths, they are sensitive to much higher layers than what we have with the iron lines. Okay, but again, it looks okay. I would say that for me, it looks fine, although it looks complex. And as you can see, there's no issue, no convergence problems, no bad pixels. So in this case, the code ran all the pixels, 231 times 231, and there's no single issue here. So I think the code is behaving very well. Okay, Han, you want to say something?
I have a question.
Okay, yeah, Alberto, yes.
Yeah, did you rerun the synthesis or just run once with configuration and nothing fails in the calcium?
Yeah, nothing fails. Yeah, it's just one run and nothing fails.
Okay.
Yes.
Thank you.
Yeah, so it's the same configuration we had from day 5. So the calcium atom that we prepare in the class, well, I think almost the same one that we prepared in RH. And it was just run synthesis, and then when it finished, this is what we had.
Okay, thank you very much.
Okay, yeah. So then after that, the last step that I want to show you today is, now we have done the synthesis. So now let's prepare everything for then run inversions. And as we did in day 5, I think, we are going to add some noise just to make things a bit more realistic. So then what we are going to do is we are going to create an array that is with the same dimensions as the array that read the output profile. So if I go back, S is read feeds of the output of the code. Okay, so just for simplicity, I multiply this by 0, and then I get an array with the same dimensions. I also load the dimensions of the wavelength vector, and then I'm going to add a noise value that it's 5 times to the minus 4 of the continuum intensity is small compared with the normal observation that we have nowadays. But some instruments already get these values, and also Visp, I think, is going to be able to achieve these values relatively easy depending on your configuration. And also, I know that the skip, for example, in Sunrise is also aiming to get this value with that given configuration. It's going to take time, integration time. It's not going to be short, but we can reach that point. So just, I wanted to have this reference that I think is a noise value that you should aim for if you are going to analyze quite some polarization signals from chromospheric lines, because they are so weak that with a larger noise, you may just have noise. Okay, and then as always, I mentioned that my impression is that the noise in the Stokes I is usually a bit larger. This could be due to different reasons. So as always, if you are just trying to replicate one instrument, for example, imagine Visp, just talk to the team that is developing the instrument, and maybe they can give you more feedback and maybe more accurate numbers. But just for this example, I just put it that from the normal noise, the nominal noise that we are going to add in the Stokes I will make it 5 times larger. But this is a bit random. So just to make, I think, the code to struggle a bit more to when making the fits. Okay. And then we just add noise. So it's the original profile plus the noise. And this is a loop that goes for every pixel. So then the noise of each pixel is different. And also the noise in each Stokes parameter is also different. And then at the end, what we need to do for the input for the inversion is to split those profiles in the number of inputs that you have in your wave grid file. So for example, if we are, just one second. So if we go to run files and we check our wave grid, so we have 3. Remember that this is the iron line, this is the calcium 8542, and this is the calcium 8542. Sorry, 8498 and 8542. So we have three windows. Okay, so then we have to do the same here. So because the code is expecting that each entrance in the wave grid file should be a separate fits. Okay, so then we just said that this iron is the cube, but only for the iron index, and we just save it with this name. And then this is the same for the calcium line. So all the calcium 8498 index, and this is the one we are going to save. And then the same here. Okay, so then with that, we have everything for running inversions. I already have done tests, so next class, we will check the results. But this is the main difference. So just we need to split in based on the number of wave grids and lines that you have. Okay, so we're going to check now some profiles, but just let me check the summary here just to be sure that I didn't forget anything. So as I said in the beginning, we already had the atmosphere in the right format from RH tutorial. So we just copied in a given folder and run the code there. It was 200 times 200 pixels. And we did the computation in NLTE. So in this case, it's full NLTE. So we call RH, and we get from RH not only the NLTE populations, but also the profile. So we get the RH profile, we adapt it to our format, but we are essentially having everything from RH. So this is as accurate as possible in our context. In my case, with 100 and 110, I think, CPU threads, it took only 2 hours. So it was really fast. As you saw, it's around 7 seconds to do. Just to have an example, is the non-LTE calcium atom plus the iron lines with a spectral sampling of 10 milliangstrom for the iron lines and 20 milliangstrom for the calcium lines. So we have 1,700, I think, wavelength points. So it's really a big cube, but still the code is really fast in that sense. So, and also, as I said, in this case, with this simulation, there was no convergence issue, no problems, okay? So then we also checked different features like the linear polarization, the magnetogram, and the continuum intensity. And I mentioned that sometimes we see some small scale, maybe wave pattern or artifacts. It's true that sometimes we can attenuate them if we improve or increase the optical depth scale sampling. So we are using now 0.1 when we did the interpolation. So if you reduce the log tau scale to maybe 0.05, you usually get maybe a bit better. But the main issue is usually the simulation itself. So when you talk to them, and if they send you similar run or the same run, but with a higher spatial resolution, you run again and then things disappear. So it's something related with the process itself. And I think it's not so bad. Sometimes it's just maybe visual because you are doing this in 2D, but I will not be worried, at least in the ones we saw today. And then we added noise. So now we have the input ready for the inversions. And I think this is basically all. So just let me show you. Well, is there any question before I show you pixels? No? Okay. So, so then in the same folder, here you have read2. And then the idea is that I again read the output. I loaded the output. So this is just the synthetic profiles, just to have the wavelength and the index. Here I'm loading the information of the wavelength just to have it for the plot. But we have our Stokes profiles already in these feeds. So I read them from the output of a previous ideal procedure. Okay, and then I'm going to plot 2 pixels, one at 0, 0, that is really, well, I would say really quite sun. So let's check, for example, for the case of the iron lines, this is how it looks. So Stokes high, you have some variation here, but it's reasonable. And then Stokes Q, and you see some variation, but basically no polarization signals. Here I kept the amplitude that we need for the next pixel, but you can see that it's almost noise. So this pixel is, we will struggle a bit to have some information about the magnetic field. And in fact, for the calcium line is even worse because it's the same. So basically noise in all the polarization parameters, but the Stokes eye profile looks fine. So just let me show you the last one. So here is the same. So basically noise and in the 3 parameters, and then Stokes eye. Okay, and then I loaded a second position that is this one that is located in the network patch. So then in this case, if we go to the iron line, this one, then you have signals. Well, so you have signals, Stokes P is very large. Stokes Q is not so large, at least in comparison with the Stokes P, but I think it's because I'm very close to the network patch, so the magnetic field is mostly vertical. But if I move a few pixels outside this, the magnetic field starts to incline, and then probably we will have more signals in the near polarization. But the important thing is that the Stokes P is more than 15%. That is a lot. And you see that the 6302 line, that is the most sensitive to the magnetic field, is already split. It's showing the 2 components of the Zeeman split. And then here things are much better for the calcium lines. So you have again, well, Stokes eye, it looks like a bit narrow, but as I said before, this is something that has been already noted regarding the simulation, that maybe much more small scale velocities are needed, but I think that's fine. And then you see that the Stokes V are large, they are above the noise patch, much more amplitude. And you see this complex in the line core, and then you have that the other satellite lines, they show also strong Stokes V signals. And the same with the calcium 8542. In this case, the amplitude is very large, comparable with the other one. And again, Q and U are basically noise, but you have Stokes V signal. So in this case, I would expect that at least the line of sight component of the magnetic field is going to be very well recovered. And then we will probably recover also something related to the horizontal component, although maybe with some error, but at least we will have something reasonable. Okay, so then I think that's all regarding today's class. I don't know if I went too fast, maybe. So just let me summarize again, maybe just, I think I don't need to say anything here. So essentially, we didn't need to learn how to prepare the atmosphere because we had it. So we just ran the code for the configuration we had. Now we have the output profiles, not only 1 pixel as before, but now for a full map. And then we are going to add noise. And in the next class, we are going to embed the profiles for the full map. And then the idea is that we are going to get from the inversion an atmosphere. And it's going to be different depending on the optical depth. So I will take the initial atmosphere, that in this case we know it because we use it for the synthesis. And we are going to compare at specific layers, for example, log-tau 0, log-tau -1, log-tau -5, where we know that the spectral lines that we are using are sensitive. And then we are going to check if what we are getting is reasonable, and if there are errors, that there are going to be errors, from where they come from. If they come from for the noise that is intrinsic to an observation, if they come from the complexity of the simulation, that is probably intrinsic from the sun. So we cannot do too much there, but we may learn how to deal at the best we can with these complex high scale variations. And also my impression is that we would learn that when you change things, in this case, you are going to compare, and then this is good because you can do it. But at some point, you should be able to say, okay, looking how the maps are looking and how the profiles are fitted, I think this is well enough. I don't need to spend too much time here. And then if you do this blindly and then compare, in this case, with the input atmosphere, you probably will get general results. And then from there, you can go to observations and trust what you get from observations. So this will be a process of learning a bit, some intuition, or learning to have some intuition, and also learning how much you can trust the code, and depending on the situation. Okay, so then, is there any question before I go back to the presentation? I don't know if I went too fast, or maybe I didn't cover things in detail, but if you have any questions. No? Okay, so then, yes, let me go back. And then, so the homework I recommend you to try is to check all the profiles we checked today. So try to copy the full folder in your server. Try to run the parallel wrap, just check that it works, check that it doesn't complain because maybe some packages are missing or things like that. If everything is working and you have some cores, like for example, 20 or 30, just run the full map and check how it looks, check if there's no converging issues. And then just get familiar with running the code. And as I said, to try to experiment. Later on with inversion is much more experimentation. With synthesis, not so much, but at least try to understand where are different things inside this the folder. So in the input files, in the atom folder, in the run folder. So what is outside, inside? Just try to get familiar with that. And then for the next class, we'll be doing inversions of the profiles that we created today. And then with that, I would say that we are going to become experts on radiative transfer and NLTE inversions for sure, because I think we are reaching, hopefully, almost the end of this tutorial. And then after that, you will be ready for doing inversions. So then next class will be in 2 weeks. And before wishing you a nice weekend, is there any question that my voice can answer? Okay, so if not, thanks a lot for joining us today, and enjoy the weekend. And see you in 2 weeks.
Thank you, Carlos. Take care.
Bye. Thank you. Bye.
Thank you. Bye-bye.
Bye-bye.
Bye. See you.